So now I'm going to talk about section 12.3. General ensembles. So there are three basic types of ensembles that can be defined for any system that is bound, any system made up of n particles. For n particle system contained in volume V and having energy E, very simply. And they include these three basic ways of describing the system: the microcanonical ensemble, the canonical ensemble, or the grand canonical ensemble. 1, 2, 3. So the most commonly encountered is the canonical ensemble. The grand canonical is used mostly for quantum mechanical systems. And the microcanonical ensemble is not used much because it is very difficult to identify and evaluate the accessible microstates in the microcanonical ensemble. Difficult to identify and evaluate the accessible microstates. However, I will talk about each one individually. So a microcanonical ensemble is for an isolated system. So in a microcanonical ensemble, you have N, V, and E that are all fixed. For a canonical ensemble, the canonical ensemble is the one that is most commonly used, so I will define it more here. It was first described by Boltzmann in 1884 and developed by Gibbs in 1902. So a canonical ensemble is in thermal equilibrium with a heat reservoir or a heat bath with specific temperature T, and the variables that are fixed for a canonical ensemble are N, T, and V. Fixed variables are N, V, and T. The system can exchange energy with a heat reservoir at temperature T. So canonical ensemble contains states of varying energy, but the system has a precise number of particles that stays constant, which means the system and the heat reservoir can exchange energy through heat, but no work will be done by the system on the reservoir or vice versa. The different states in the ensemble will have different probabilities depending on their total energy. So let's write that down very briefly. Canonical ensembles contain states of varying energies, but the system has a precise number of particles that remains constant, which implies system and reservoir can exchange energy through heat, but no work will be done on the system or by the system. And that implies different states in the ensemble have different probabilities depending on their total energies. So again, recognize this is going to be a closed system. A closed system is a system in which heat energy can be exchanged, but particles cannot. Now, the grand canonical is an open system which can exchange energy with a heat bath as well as the particles with another reservoir. Now, in this case, we have uncertain number of particles which is in thermal, because the system is in thermal and chemical equilibrium. So that means that a grand canonical ensemble can exchange both energy and particles with the heat bath of a specified temperature T and chemical potential mu. The different states in the ensembles are accorded different probabilities depending on their total energies and the total number of particles. And in the grand canonical ensemble, the constants are mu, V, and T. And the basic type of grand canonical ensemble is actually in a chemical reaction where the number of each molecular species is not conserved. In a chemical reaction, the number of each type of atom is conserved. However, the number of each type of molecule is not necessarily conserved. Other examples in nature where the number of particles are not conserved include black body radiation, particle annihilation, and decays of particles. So that brings me to the end of the discussion about the canonical, grand canonical, and microcanonical ensembles. If you guys want to read more, I suggest read a thicker textbook, but that's what the fundamental idea is of these three ensembles. And there's a lot more math that can be done with them to explain all the details. So, but I want to talk about one thing before we leave. Thermodynamical ensembles do not give identical results always. For example, important cases where thermodynamical ensembles do not give identical results include microscopic system, large systems at phase transitions, and large systems with long-range interactions. However, in those cases, we have to choose the correct thermodynamical ensembles in order to figure out what the answer is going to be. For systems that are made up of large number of particles, generally all three ensembles tend to give identical behaviors. And then it's then just a simple matter of mathematical convenience which ensemble is used.